Hello everyone, this is Jayashree Shedvarkar, Assistant Professor, Department of CSE, KLS PDIT Hadiyar, welcomes you for the lecture series on Computer Graphics and Visualization, Module number 3, Lecture number 21. Contents covered in the previous lecture are: from the second module, we have discussed the lab program, rotate the triangle about origin and about its fixed point. So we have discussed the program with the matrix representation by using some transformations followed by translation, rotation and inverse translation. And also we have written the program by using OpenGL functions to translate, rotate and inverse translate by using GL translate F, GL rotate F inbuilt function in OpenGL. Today we are going to discuss about the two-dimensional weaving pipeline, the clipping window, normalization and viewport transformations. So with this we'll be able to learn two-dimensional weaving with the clipping window. Let us first understand what is clipping window. Whenever we design our own clipping window with any shape, size and orientation, we can choose any size and shape. So the clipping window normally can be chosen by the size rectangle size, because which is going to cover almost all area once the object is clipped by a clipping window, compare with other shape and size of the clipping windows. So better to design the clipping window with rectangular shape. And which is the best use of that clipping window considering with our designing of any of the clipping window. Let us move to the clipping of a scene using concave polygon or a clipping window with non-linear. Boundaries require more processing than clipping against a rectangle. So because of that, rectangular clipping window is in a standard positions are easily defined by giving the coordinates of two opposite corners of each rectangle. So rectangle will be designed in such a way that if it is a rectangle, this is for in the example you can see, once if we give just the two coordinates, two corners of the rectangle if we give, it is able to draw the rectangle. So because of this thing, rectangular clipping window is in a standard position. So because of that, we require less processing time clipping against a rectangle if we compare with other clipping boundaries or other clipping shape. So let us move to how to view that coordinate clipping window. As a general approach, the two-dimensional weaving transformation is set up in a weaving coordinate system. Weaving coordinate system that we are going to consider within the world coordinate frame. Already we have discussed the two-dimensional pipeline. So from that world coordinate to weaving coordinates we need to convert. So to convert from world coordinate frame, that is world coordinates to the weaving coordinate system. To do that, you can see in the example in this figure, world coordinates will be represented in the form of x world coordinate and y world coordinate in two dimension. This same thing will be converted into weaving coordinates. The weaving coordinates are given or set up in the form of this direction, that is shown in the figure x view and y view. So among this x view and y view, now this will be converted or transformed into weaving coordinate from the world coordinates. In the weaving coordinates, we are trying to draw a clipping window of rectangular shape. So that now within this clipping window, whatever the object is going to appear within this clipping window will be consent for the rasterization. Other parts lying outside of this clipping window will be erased off or not sent for the rasterization, that is for display. So we choose our origin for a two-dimensional weaving coordinate frame at some position x0, y0. Here we can consider this is our position which is going to start with our original position. From the world coordinate we have chosen x0 and y0. So this will be our starting point p0 which is going to have x0 y0, so that we can establish the orientation of using a world vector v that is going to define the y view direction. So in which direction it is going to be viewed. The vector v is called as two-dimensional weaving vector or two-dimensional weave up vector. The alternative method for specifying the orientation of the weaving frame is to give a rotation angle relative to either the x-axis or y-axis in the world frame. So either we are giving the weave up vector or else the rotation angle. The rotation angle needs to be considered either from the x-axis or from the y-axis. In this direction, here it is been given some rotation angle r. So depending upon that, a rotation angle is relative to either x or y axis in the world frame. The first step in the transformation sequence is to translate the weaving origin, this weaving origin, to the world origin. Then we rotate the weaving system to align it with the world frame so that we can rotate. So this is what actually our weave coordinate system, so that we can rotate this weaving coordinate so as to align with our world frame, so that it will be very helpful or to consider the components of unit vectors such as Vx and Vy, and U is component related with the x weave axis, Ux and Uy. So V is a related with y weave axis and U is a component or vector which is related with x axis respectively. So where we are going to apply the translation as well as rotation, what we have discussed in our previous module, T is a translation matrix. We are going to apply how much the translation distance we need to add as a vector, and the rotation matrix, how much angle we are going to consider for the rotation. So that depending upon these two matrices, a weaving coordinate frame is moved into coincidence with the world frame. This weaving coordinate is going to coincide with the world frame as shown below. So that now the world coordinate will be converted into weaving coordinates. Now we are going to extend this world coordinate clipping window. A routine for defining a standard clipping window in world coordinates is typically provided by some graphics library, and we are going to simply use two world coordinate positions which are assigned to the opposite corners of a standard rectangle. If this is a rectangle we have chosen, this is a clipping rectangle, either this end or these two corners we have to give for standard positions. Once the clipping window is been established, the screen description is processed. Whatever the screen you want to display within the clipping window will be get processed. Other part which is going to lie outside of this clipping window will not be sent for the display. That thing can be done by using some through the weaving routines to the output device, so that we can simply rotate and possibly translate the objects of a desired positions and set up the clipping window all in coordinate positions. So here we can see in the example, this is a triangle in the first figure with a selected reference point and a orientation weave up vector that is to be translated and rotated to a position, so that which is going to lie within the world coordinate frame. If we consider that thing, some translation if we applied and rotation we have applied for this object, that is triangle object, that is going to fit within the clipping window, so that this triangle entirely lies within the clipping window, so that this triangle will be sent for the output. Then the triangle will be displayed on the screen. This is how actually the world coordinate reference frame takes the object to display onto the screen. Next, once the weaving coordinations have been done, it is better to go for the normalization and viewport transformations. The viewport coordinates are often given in the range between from 0 to 1, so that the VWAP positioned within a unit square will be considered. After clipping, a unit square containing the viewport is mapped to the output display device. So that mapping has to be done with a clipping window into a normalized viewport. We first consider a viewport defined with normalized coordinates ranging from 0 to 1. This is what the normalization viewport, ranging from 0 to 1 in x direction as well as in y direction. And the object descriptions are also transformed. This is what the object description we want to transform. According to this example figure, the object we are displaying within the clipping window is point, which is having xw and yw as a coordinate. That will be transformed to a normalization viewport. So that normalization viewport, once it is normalized, so using transformations which is going to maintain some relative placement of a point within this viewport, and which is to be mapped with exactly the clipping window position of xw and yw. In the clipping window is mapped as, here we can see it is xv and yv, which is associated viewport depending upon the normalization viewport. So that this point xw yw is now mapped to a normalization viewport, that is xv and yv. So this thing can be done by using normalization and viewport transformation matrices. To transform those world coordinates, what we have discussed in the previous slide, how to transform a world coordinate to viewing coordinate, then normalized to some relative position. And whatever the viewing coordinate position will be there, it should map with some same relative position in the viewport also. Then only we will be getting the exact object onto the screen. Otherwise it is not possible. So to map those things or to transform that world coordinate point into the same relative position within the viewport, we need to do some calculations. So that thing can be done using this equation from the previous figure. That is xv minus xv min divided by xv max minus xv min. This should be proportionally equal to xw minus xw min, xw max minus xw min. Same thing, these values will be calculated with the y-axis. Once if we assign or map these values from coordinate position, world coordinate position to the relative position within the viewport with x values as well as y values, now we can calculate the equations for viewport positions. Viewport positions we have considered is x, v and yv. That thing will be done by applying some scaling and translation matrices using these equations. So that thing will be calculated as xv is equal to sx into xw. This is x coordinate, world coordinate value for the x-axis and some translation distance according to the x-axis. Same thing will be calculated yv, that is y coordinate with the viewport position. That thing will be multiplied with the scaling factor of y-axis into yw, that is world coordinate of the yw, and added with some translation distance according to the y-axis. So this equation will solve us and will give us the viewport position which is mapped exactly with the world coordinate point, where these sx and sy parameters are considered as scaling factors. These scaling factors are calculated depending upon our viewport position as well as the world coordinate points. So this thing will be calculated as sx is equal to xv max minus xv min divided by xv max minus xw min. So this is related with the viewport and this is related with the world coordinate point. Same thing, SY parameter is calculated depending upon the y-axis, and translation factors are calculated as Tx and Ty, where it will be calculated as XW max XV min minus XW min into XV max divided by XW max minus XW min. Same thing will be calculated for Ty. So once Sx and Sy parameters and Tx and Ty parameters are calculated depending upon our world coordinate point as well as the viewport positions. So we are going to use those calculated value in these equations. So once if you substitute all the values Sx, Sy parameter, Tx, Ty parameter, which is going to calculate the new relative position within the viewport, and exactly this new relative position within the viewport is mapped with a world coordinate point. To do that thing, so we need to solve all these equations. So we could obtain the transformation from world coordinate to viewport coordinates with the following sequence. First, what we have done is scale the clipping window to the size of the viewport using a fixed point position. Fixed point position will let us consider as world coordinate x-axis and y-axis, and translate some distance xw min, yw min to xv min and yv min. So this is to be continued with the scaling transformation. Already we have discussed the scaling transformation with a two-dimensional matrix according to the homogeneous coordinates as S. S is a scaling matrix, whereas Sx and Sy parameters are considered as scaling parameters Sx and Sy, and depending upon the fixed point position, that is xw min, yw min will be calculated depending upon the fixed point according to this matrix. Same thing, two-dimensional matrix representation for the translation of the lower left corner of the clipping window to the lower left of the viewport corner will be mapped with according to this translation matrix. Once if we composite these two matrix representation, so we are going to get the matrix representation for transformation to the normalized viewport. So this is a transformation for the window depending upon the normalized viewport will be calculated as multiplying T and S parameters. T is a translation matrix, S is a scaling matrix. Once if you multiply T into S, we are going to get the composite matrix representation for the normalized viewport. So this is what the normalized viewport matrix representation, where the diagonal elements are Sx and Sy parameter, and the third row values are Tx, Ty and parameters, and one is a homogeneous coordinates. So once that mapping is done, so that thing will be exactly converted into normalized square. So another approach to two-dimensional weaving is to transform the clipping window into a normalized square, so that a clipping in normalized coordinates will be transformed through the scene description to a viewport specified in screen coordinates. So that transformation will be considered depending upon the normalized coordinates. That normalized coordinates always will be ranging between the -1 to 1. So if we consider our normalized square depending upon -1 to 1, so how to map this clipping window to the viewport? So we are applying this values, normalized coordinate values -1 and 1 to the scene, so that our matrix for the normalization transformation is obtained by substituting in the previous equations with the value xv min as -1 and +1 as xv max. Once if you substitute all the values in our previous equations, and if we try to calculate the equations for Sx, Sy, Tx and Ty, then we can multiply S and T, so that we are going to get this matrix of for normalization transformation this is only within the range from -1 to 1. So this is another way to consider the normalized square. Either the normalization square will be considered from 0 to 1 or else from -1 to 1. Both way can be done to consider the normalized square which is mapped from the clipping window. So once if you are done with all those things, the clipping algorithms must be applied and the normalized square with the edge always length equal to 2 and is transformed into a specified viewport. So we are going to get the transformation matrix by substituting these values -1 for W min and YW min and substituting +1 for W max and for X value and Y value. So that we are going to get this matrix. Once if you substituted all the values, we are going to get this is a normalized viewport depending upon -1 to 1. So once if we are done with all these things, so this is what actually the normalized coordinates square for displaying the object. Typically, lower left corner, this is the lower left corner of the viewport is placed at the coordinate position. So coordinate position will be considered normally as a lower left corner. So this is the first end. This is a lower left corner. So this is what the gray window is considered as our display window. Within that our viewport coordinate has been set up, X and Y axis. So this is considered as origin. So this figure demonstrates the positioning of the viewport within a display window. So now within the viewport, the rectangle has been drawn. So this is considered as an clipping window. Within that one triangle object is displayed. So that why this is displayed is that triangle entirely lies within the clipping rectangle. If it exactly any geometric object lie within the clipping rectangle, that will be sent for the display. So that which is going to display on the display window. Other part of the object which doesn't lie within the rectangle, if it lies outside of the clipping rectangle, that part will be discarded and not sent for the rasterization. Means that will not be get displayed within the window. So this is how it converts the mapping window into a normalized square, that is clipping window. So to display characteristics, even same thing can be handled in one or the two ways that are mapped through the weaving pipeline to a viewport. Simplest mapping contains some constant character size or what are all the character patterns we may use. So different character patterns consisting of some fonts or else some shape or size. Depending upon the outline character shape, that thing will be used to display any of the character strings also. So which is going to display the character onto the screen, which splits the screen effects and multiple output devices. So that thing can be done by using a mapping to a selected output device is sometimes referred to as workstation transformation. That thing can be done by using selecting different clipping windows, associated viewports for a scene. We can provide simultaneous display for two or more objects, multiple picture parts or different views for a single scene. So it is made possible that two or more output devices could be operating concurrently on a particular system, so that it is very easy to set up a clipping window and viewport pair of a device. So in the today's class we have learned two-dimensional weaving pipeline, how to set up the clipping window, how to design our own clipping window with any shape, size and orientation, and how to normalize to the viewports and how to map the clipping window into normalized viewport into the square, so that we'll be able to understand the 2D weaving with respect to weaving coordinates according to the clipping window. According to this class, the important questions on this topic are: explain two-dimensional weaving transformation pipeline, explain how to map the clipping window into normalized viewport, explain how to map the clipping window into normalized viewport into square display window. Additional links we can refer. You can refer the textbook, Donald Hearn Pauline Baker textbook, chapter 6, the subsection 6.1 to 6.3, page numbers from 296 to 306.